Okay, so welcome to our tutorial on worked problem on equilibrium, where remember equilibrium has to do with something called delta G naught, or the free energy change. And so the naught tells us that it's a standard state, and I've just highlighted that, and I'm now writing out some of the conditions that define this standard state. So we have a temperature of 298 Kelvin, pressure of 1 bar, which is about equivalent to 1 atmosphere. And then we're also going to have activity, which you'll recall is, for the purposes of this course anyways, equated to concentration. So we're going to have activities that are fairly dilute, so just 1 molar. And these are conditions that we take when we talk about standard state. And so the free energy change, which has to do with G, or the Gibbs free energy, tells us about the energy change that is associated with a chemical reaction and that can be used to do work. And as we'll see, this is a very useful concept. So what are some of the things that we can learn? So based on the sign of delta G naught, for instance, which I'll just write out here. So delta G naught, whether it's positive or negative, that will tell us something about whether the reaction in question is spontaneous or not. And you can go back into the lecture notes to review, but as we found in class, a negative standard Gibbs free energy of reaction indicates that the reaction in the forward direction is spontaneous, that is, product formation is favored. And as for the magnitude, well, what does that tell us? The magnitude of delta G allows us to determine what I'll call here the equilibrium ratios. That is, how much, in terms of concentrations or partial pressures, of products and reactants we have at chemical equilibrium. And it's important to remember that we can think of equilibrium quantitatively in terms of what's called the equilibrium constant, or K sub EQ. And I will refer you to lecture note number 19 for a thorough discussion of relevant equations that relate delta G naught to KEQ, and also the difference between delta G naught and delta G, which will then allow us to move on to just a brief analogy. And so I omit this extra material because while it is extremely important, and I would strongly suggest that you go back and look at it, you do not technically need it to solve these problems. So for the sake of time, let's move on. Last thing I wanted to leave you with before we actually work our practice problem is an analogy of delta G naught and delta G as a kind of topographical map. So a map that allows us to look at the energy landscape for a given chemical process. And so to illustrate this, here is a map. I believe this is of North Carolina, but anyways, you can see that there are clear features, right? So there is this ridge, as indicated by the purple line, and there are different routes that we can take to get from, say, the top of this crest down into the valley, which I can draw by an arrow here. And so what delta G allows us to do for chemical reactions is to determine ways in which energy is likely to be distributed or provide directionality for a process given a specific set of starting conditions. Note, however, that this tells us nothing at all about how fast we'll get there, right? That we'll have to wait until we get to the realm of kinetics, which we will discuss after exam 3. But thermodynamics, while being extremely useful in terms of planning and predicting what will happen, can not help us with the rate. And so just as a brief illustration, you can imagine that kinetics would allow us to take one method for getting there, right? So a donkey. Or we could take another route, which would be apparently this supersonic NASA jet, but delta G itself tells us nothing about which way we will choose. So now to go on to our problem, we first are asked to calculate Q, the reaction quotient. And so I'll just look, and it's the ratio of the products. So I have partial pressure of hypochlorous acid, and I'm going to square it because that is the stoichiometric coefficient given in the reaction. And then on the bottom, we'll have the partial pressures of the reactants, so water vapor and Cl2O in gaseous form. And I just want to highlight that the reason why I'm using partial pressures here is because both the reactants and the products that are participating in this chemical process are in the gaseous state. And so were this happening in aqueous solution instead, we would use concentrations or whichever one was appropriate. Now in this case, you can see I'll just put in the numbers that are given. And so remember that the reaction quotient and also the equilibrium constant, KEQ, are defined in terms of activities, which ultimately makes them unitless. But in this case, conveniently, the units cancel out, and when you're working problems on the exam, I would say be mindful of units for sure, but in general, just remember that your final answer will be unitless, and that's because we've made this substitution or approximation, which is generally valid for the conditions that we're dealing with. So my answer here, which I'll just box, is 0.011. And so we can move on to part B, which asks if the system in part A is at equilibrium. And so in order to do that, let's recall delta G naught and as it relates to KEQ. And so just to correct what I said earlier, I stated that the naught symbol indicates that we are at standard state, which is misleading and a bit of a misnomer. So it indicates that we are at standard conditions. Standard state, you might remember, is often used to describe the standard state of the elements in terms of Gibbs energies of formation. So just to clear that up. So we know the constant R, we're given the values for delta G and for temperature, and so I've just plugged in the numbers and solved for the equilibrium constant, and I see that it is greater than Q by a significant amount, which allows me to conclude that this system is not at equilibrium, because if it were, KEQ would be equal to Q, the reaction quotient. And so since they are not equal, my answer is no. And then in terms of predicting which direction, I will say that it will go towards products. And this is because if we want to reach equilibrium, in which case Q is equal to K, we would need to increase the magnitude of Q, right? And so we will do that by either increasing the numerator or decreasing the denominator, and that will be achieved by creating more products from the reactants that we have. So to move on to question 6, I have to remind ourselves of the famous principle proposed by Le Chatelier, which allows us to make qualitative predictions, so as a kind of complement to the quantitative predictions that we were able to perform in problem 5 based on delta G, values for KEQ, values for Q. Le Chatelier's principle is useful in terms of thinking about what direction a system in equilibrium will move in reacting to applied stress. And so we can paraphrase this principle by saying a system in equilibrium will react to stress by acting in a way as to minimize it. And so how does this carry itself out? Well, for problem 6, part A, what happens for this given reaction if HI is removed. So first, sometimes it can be helpful to identify what the stress is. Well, in this case, I would say the stress is the decrease in the hydrogen halide. So in this case, we're removing HI from the reaction vessel. And so this, by Le Chatelier's principle, should shift the reaction towards products. So if we are removing product, the system in equilibrium will shift to form more product so as to reduce the stress of loss of product. You can also think of this in terms of Q and K. And so if we remove HI, we are decreasing its partial pressure in the container. And this will decrease Q if you write out the reaction quotient expression. And so because the system will then have a Q that is less than K, it will shift towards products. And so a handy mnemonic device is if you write Q and K in alphabetical order and draw the relationship between them, greater than, lesser than, or equals, you can imagine that as an arrow pointing in the direction that the system will go towards. However, again, I would stress and strongly recommend that you go back to lecture notes 19, as this provides the actual basis for all of these more soft or mnemonic devices. So for part B, just to finish up quickly, we have helium, which is an inert gas. So this is key. We need to recognize that it is not participating in the reaction, and thus that the partial pressures of the reactants and the products in our system will not be affected. And this goes back to the definition of partial pressure, which you can find in your textbook. And so because the partial pressures of both products and reactants are unchanged, we will see ultimately no shift in terms of the reaction. And so I will just conclude by boxing answers and noting that any alternate valid explanation would be fine. So whichever works for you. And I will call that good.